Hey, welcome back. This is 7.1, finding the area between two curves. And we begin with some pictures of what's going on. So area of a region. And first, just thinking visually. And I think of it like the donut hole problem. So if you want to know the area of a donut, what you do is take the area of the outer part and then subtract away the area of the donut hole, and you end up with the area of the donut, right? Okay, it's the same idea here. It's just now what we're going to do. It's kind of the same idea, though. Okay. I'm going to sort of subtract these two and end up with the area between two curves. So let's get two curves going. Call this one G. This one F. So to get the area in here, what you're going to do first is find the area below the curve F. I'm trying to draw that as best as possible. And we're looking for the area from, let's say, A to B. Okay, so I get the area underneath here. I know that looks like a plus, but it's supposed to be F. Then I subtract away the area underneath G. So that would be something like that. And what you end up with is the area between the two curves. Okay. We have formulas for finding out the area underneath these curves. It's the integral, right? So the integral, and again, these are from A to B. The integral of f of x dx from A to B minus the integral of g of x dx from A to B is going to equal or be the same thing as the integral of f of x minus g of x dx from A to B. Okay. You can go about this theoretically and think of the Riemann sum as an accumulation of rectangles. Okay, so maybe theoretically, let's call it. And what's happening here is that we are trying to add up all these rectangles. Let's take a generic one out here in the middle, all the way to the end. So the area of this particular rectangle, let's call him A sub I, the area of that guy is going to be, if you consider this position x sub I and the width of this rectangle change in x, then the area will be, and then let's call the top curve F and the bottom curve G, it'll be f of x sub I, basically the height of the rectangle from the base all the way to F, and then minus the height of the rectangle all the way up to the G graph. Okay, so maybe put that in red, that height right there. That gives you the length of this rectangle here. Maybe let's put it in blue or maybe yellow. Okay, this rectangle. And then you just multiply it by the base, which is change in x. Okay. Or change in x sub I if you have varying intervals of width. Then for the Riemann sum, all you got to do is take the, an approximation of that area would be the sum of all those rectangles. But then we could take the limit of that as the number of rectangles goes to infinity. So going from n equals, or I equals 1 to n. And of course, we just end up with the integral that you see above there, the integral of f of x minus g of x dx from A to B. And as you read your book, you see basically my visual kind of representation there. That's what I did in 7.2. That was my visual part. Then you'll come down here, and this is kind of the theoretical part. Okay, so they actually call these delta change in i's. So I put a little delta in there just to be consistent with the book. And you see the formula is just from geometry. It's the area of the rectangle is base times height, or in this case they say height times width. Then they go ahead and add up all the rectangles, take the limit as n goes to infinity. This norm stuff, the norm going to 0, that was the length of the biggest subinterval. If you go back and read your stuff on Riemann sums, you'll see that. But it's the same as taking the limit as n goes to infinity if you assume all of your change in x's are the same. So I guess I don't need the change in x sub I right here. This part I don't really need that. Okay. Okay, so then they're just saying basically what I just said. Take the limit of it and you'll end up with this integral. There's some conditions. F and g have to be continuous on a and b, and they want f of x to be the top curve and g of x to be the bottom curve. So in general, I would say when you're setting these up, in general, you'll have sort of an integral from a to b of the top curve minus the bottom curve. Okay, and then hopefully that will give you some intuition, some geometric intuition. So when I say top and bottom, I always, kind of think of this Riemann process as like a guy running across in this direction when we're with respect to x. He's running across and he's kind of picking up all of these areas, all these delta a sub i's, and he's putting them in his bag. In this orientation, you can see that the top curve is kind of like the top of the house, and that would be f, and then the bottom curve is this green curve here, g. Okay, so hopefully that's clear. So this will work even when your rectangles go below the x-axis, because in those cases, when you do your difference between the top curve and the bottom curve, you'll have, so like in this case, at this position here, we need this big rectangle here for our Riemann man, I guess, or accumulating guy, as he runs across in this direction, picking up the rectangles. Okay, so to get that value, that length, it's f of x sub I minus g of x sub I, and basically what you'll get is just the distance from the x-axis to f, and then minus the distance from the x-axis to g, but the distance from the x-axis to g, it's going to be a negative value because it's just given by whatever g of x is. So you're going to have this f of x minus this g of x, but g of x is negative, so it ends up being a sum. So it's the red distance plus the blue distance here, and that gives you the length of that rectangle. So it works even though you're going below the x-axis. Okay. This is not a foreign concept. The truth is, every time you figure out the area underneath a curve where your function is positive, so if you're figuring out the area underneath this curve, f of x, and note my curve f of x is above the x-axis from a to b, technically you are figuring out the difference between two curves. It's just one of the curves is g of x equals 0. Right? It's just the x-axis. So in your integral to figure out the area underneath f of x, we know it's just f of x dx, but technically you could think of it, you could reimagine it as f of x minus 0 dx. And so it is a difference between two curves. It's just one of those curves is 0. Okay. Okay, for the most part, when you're working then in the homework here, like example 1, you're probably going to need to graph the thing and see what you're looking at visually. Okay, so literally graph it using your calculator. There's some things you should be able to graph at this point without a calculator, like parabolas and straight lines. I would expect you'd be able to do those. So let's look at example 1. We want to find the area of the region, and it's in the book here on the right. Find the area of the region bounded by the graphs of y equals x squared plus 2 y equals negative x equals 0, and x equals 1. Okay, so I'm going to graph it. The graph of x squared is just a parabola with 0, 0 at its vertex. Plus 2 is going to shift it up 2 places, so you end up with this graph here. Y equals negative x is a diagonal through the origin, and it's going downwards. We started drawing it upwards, but it goes downwards. Okay. X equals 0 is a vertical line. It's the y-axis. I'm drawing it in red. X equals 1 is a vertical line as well. I'll draw it in blue. And then we're trying to find the area enclosed by all those curves. And it's a little tricky sometimes. In this case, it's kind of obvious. It's just this region here. Okay. Okay, so this one, fairly simple. I'm just integrating from 0 to 1. And you could always draw a little Riemann man, running man, so you have the orientation correct. And he's running in this direction. The top curve will be the parabola x squared plus 2. The bottom curve minus negative x, and then dx. And the Riemann man is collecting rectangles going from 0 to 1. So he's collecting those areas from 0 to 1. And then you can go ahead and get some practice integrating. Let me rewrite it so it's in sort of a familiar form. Go ahead and integrate using power rule. So x cubed over 3 plus x squared over 2 plus 2x, and evaluate now from 0 to 1. So it's going to be 1/3 plus 1/2 plus 2 minus 0, 0. They're all 0, so just minus 0. Find a common denominator. So this would be 2/6. This would be 3/6. This would be 12/6. So 5 plus 2 is 17/6 for the area of that region. Okay. Okay. Let's move on to finding the area between intersecting curves. So in this case, we're able to kind of just look visually to get the boundary. The boundary was marked off by these two vertical lines, x is 0 and x is 1. If you look at my first example, they don't really have boundaries beyond where they intersect. Okay, so you'll have sort of one additional step to do, and that's to set the equations equal to each other and solve for the boundaries on your integral. So let's look at example 2 then, and we have some graphs. F of x equals 2 minus x squared, and then g of x equals x. I'm going to graph it and see what it looks like. So the graph of x squared is this. The graph of negative x squared just rotates it about the x-axis. And then adding 2 will shift it up 2 positions. Okay, so there it is. So 1, 2. Its intersects are at plus minus square root 2, which is out in front of 1 somewhere, so it looks like this. And then g of x equals x, that's a diagonal through the origin. Okay, so we want to find the area between those two curves, and that's this region. In order to find where they intersect, the x values where they intersect, I'm going to set the two equations equal to 0. Or set the two equations equal to each other. And then I'm going to solve. Okay, so I just set x equal to f, g of x equal to f of x. In other words, x equals 2 minus x squared. So there's g of x is right here. This guy I put over on this side for some reason. Okay, so set it equal to 0. X squared plus x minus 2 is 0. Factor x plus 2, x minus 1 is 0. Solve, so x is negative 2, x is equal to 1. And those become the limits on your integral. So again, thinking of our Riemann man, our running man going across, picking up all these little areas of rectangles. He is running from x equals negative 2 to x equals 1. Okay, the top curve is the upside down parabola. The bottom curve is the diagonal. And then you're just power rule. So I'm getting the antiderivative. Then evaluate that at the limits of the integral. Okay. So I'll go 2 minus 1/3. So always have to deal with some fractions. And then minus 4 minus 8/3 minus 4/2. A little bit of arithmetic, right? So what do we got? 2 minus 1/3 minus 1/2 minus 4 plus 8/3 plus 2. Okay, so -4 plus 2, that's all 0. Looks like I got a 7/3 minus 1/2, assuming I didn't make any mistakes. So this would be 14/6 and 3/6, so 11/6 for my answer for the area. Whoops, I made a mistake. Let's make sure I got it set up right. Yeah, I must have made an arithmetic mistake here. So -4 plus 2. 2 plus 2 is 4, minus 4, that's fine. And then I got -1/3 plus 8/3 is 7/3. And then minus 1/3 plus 6/3, no, plus 8/3. So that would be 15, that's 14/3. 15/3. Okay, sorry. So what did I do? Oh, that's a -2, no wonder. So this would have been plus, because the cube of a negative is negative, and then there's a negative in front of it, so that'd be plus. This would be minus. And then we have -9/3 minus 1/2. So -18/6 minus, I guess, 3/6 is -21/6. Divide top and bottom by, it's still wrong. Oh my God. Okay, so this also is -4. Let me get rid of all this junkola. Who would have thought this is the most challenging part of the integral, you know? Just doing the arithmetic. Good. Okay, let's try this one more time. I swear I'll get it this time. 2 minus 1/3 minus 1/2 plus 4 minus 8/3 plus 2. So this would be 4, 5, 6, 7, 8. This is -9/3 is -3, and then minus 1/2. So 5 minus 1/2 equals 10/2 minus 1/2. Ugh, 9/2. There it is. Okay, great. Let's look at another one. This one we have find the region between. They want to find this purple region here in figure 7.7. So example 3, we have y equals, or I guess f of x is sine of x, and g of x is cosine x. Let's go ahead and graph them. So pi over 2 pi, 3 pi over 2, 2 pi. So sine starts at 0, goes up, comes back down like that. And then cosine starts at 1 and then does one of these jobs. Okay. So we want to find this region here. Sort of remind yourself of the Riemann man running, collecting these rectangles. Let's put a rectangle in there. So the top curve looks like it's going to be the sine of x, and then the bottom curve is going to be the cosine x. Okay, we need to find the intersection places, so you may have a little bit of trig to worry about. Let's remind ourselves this is pi over 2, this will be pi, 3 pi over 2, and then 2 pi. So sine x equals cosine x, and I want to solve this on the interval from basically 0 to 3 pi over 2. There should be 2 solutions, 2 x solutions. Okay. You can divide both sides by cosine in that interval, and it we get sine x over cosine x. So we're assuming that cosine is not equal to 0 in that interval. So that'll equal 1. So you have the formula tan x, or the equation tan x equals 1, and then you're thinking of solutions on 0 to 3 pi. Okay. So tan of x is equal to 1 at pi over 4. So x equals pi over 4. But also at this guy right here, so 1, 2, 3, 4, 5 pi over 4. And those will be the limits on your integral. So again, the top integral was the sine x, and the bottom integral was cosine x dx. And then we're going from pi over 4 to 5 pi over 4. Get the antiderivatives. So negative cosine x minus sine x pi over 4 to 5 pi over 4. And so negative, 5 pi over 4 is in the third quadrant. The reference angle pi over 4 is going to give you root 2 over 2. We just have to see what cosine. So cosine in that quadrant is negative, so it's negative root 2 over 2. Then minus sine in that quadrant is also negative, so negative root 2 over 2. And then minus cosine in the first quadrant for pi over 4 is positive, so that would just be negative root 2 over 2. And then sine is also positive in the first quadrant, so minus root 2 over 2. And then what do we have? Root 2 over 2 plus root 2 over 2 plus root 2 over 2 plus root 2 over 2. So there's 4 root 2 over 2's. So you get 2 root 2 for your final answer. This next guy intersects in more than 2 points, so they give you a nice little picture here. I probably wouldn't expect you to be able to draw cubics out by hand on a test. But let's take a look here. So this is example 4. One curve is 3x cubed minus x squared minus 10x. G of x is negative x squared plus 2x. I mean, you could do these by hand. It's not really a big deal. Set it equal to 0. You can factor out an x. So you get 3x squared minus x minus 10. And you could probably factor that. 3x by 2, right? And then 5. And then you want the bigger one to be negative, x, and then plus. So x is 0, x is negative 5/3, x is 2. It's cubic, so the end behavior will be like this, and then it'll do something, and then it'll go out like that. So at negative 5/3, which is less than 2, so here's 3/3, 4/3, 5/3, 0, and then 1, 2. So it should have some sort of behavior like that. Oops, yeah, should be smooth. There's no weird kinks in it. The other guy, you could factor out an x, a negative x, even better, x minus 2 left over. So 0 and then 2, so 0 and 2, and it is a parabola, so it's probably going to hit like that and then do something like this. Okay. So I'm expecting 1, 2, 3 intersects, and I'm trying to find the area here that's contained by the two graphs. Okay. So to get the intersection points, I'm going to set the equations equal to each other. I hope that's painless. So what do I got? I'm going to move the x squared over, so I got 3x cubed. Oh, the x squares cancel. Move the 2x over, so minus 12x is 0. Bring the 3x out, you get x squared minus 4. Then you can continue factoring that because it's a difference of squares. And you get the 3 intersection points, one at 0, one at negative 2, and one at 2. So it looks like you're going from negative 2. The Riemann man is running from first -2 to 0, and you need to be careful with the orientation, right? So the g of x and the f of x are going to change with regards to who's on top and who's on the bottom. So first off, f of x is on top, so you have the 3x cubed minus x squared minus 10x minus the negative x squared plus 2x for the first integral. And then you need another integral, so plus going from 0 to 2, and this time the g of x, if you think about the Riemann man running through here, sort of trying to draw the Riemann man, as he runs through there, the top curve now is the g of x, so negative x squared plus 2x, and then minus the 3x cubed minus x squared minus 10x. Okay, so you have to have two different integrals because of that fact. You can't just use one. Okay, so let me simplify this deal. So going from -2 to 0, 3x cubed, the x squares will cancel out, and then you have -10 minus 2, so -12x dx, and then plus this other integral from 0 to 2. The x squares are going to cancel again, and you're going to get 12x minus 3x cubed. So this should be a 3x cubed. I don't know what I'm doing. Sometimes it's a cube on there. And then dx. And then we should be able to power rule it. So 3x to the 4th over 4 minus 12x squared over 2, so 6x squared, from -2 to 0 plus pretty much the same thing but with different signs. So 6x squared plus 3x to the 4th over 4 from 0 to 2. Okay. Put in the limits of the integral. So putting in 0, you just get 0 minus 0, and then minus plugging in 2. 2 times 4 times 2 is 8, 16. All over 4 is 4 times 3 is 12. Minus 4 times 6 is 24. And then I should get the same stuff just with opposite signs, right? So putting in 2 first to get the 24. And then minus, whoops, I lost a sign there. This should be minus. So 24 minus 12, yeah, and then minus 0. So I get -12 plus 24 plus 24 minus 12. And it looks like I get 48 minus 24, which is 24. Okay. Okay, good stuff. And then they're reminding you top curve minus bottom curve. Okay, this next part, what they're going to do is change orientation on you. So rather than having these kind of Riemann man running across and picking up these vertically oriented rectangles, going across the x-axis. Now they're going to run them up the flagpole, so to speak. So let's call this, I guess, section 2, horizontally oriented rectangles. So the deal is you'll have some sort of, it's basically a non-function scenario. So by a non-function, I mean it fails the vertical line test. So you can see here, this guy would fail the vertical line test because it hits it in 2 places. Right? So doing it in your normal way with the Riemann man running across the x-axis isn't going to be efficient. You could do it, but it's going to be a nightmare. So rather than doing it that way, what they're going to have you do is kind of run the Riemann man up the flagpole. From our normal orientation, it looks like the rectangles are horizontal. But if you think about the Riemann man going sort of, quote unquote, again, up the flagpole, he is accumulating the rectangles in the same way that he did in the above pictures. Okay, you just have to make sure he's oriented correctly. So in this case, it's left and right. Okay, the right curve will be your top curve, and the left curve will be your top curve, and the right curve will be your bottom curve. Okay, so this is, let's give these guys a name. Let's call this one, I guess, G, and call this, well, let's call this one F, right? Let's keep that as the top. and this one is G. So in this orientation, you could see that the top is going to be this red curve, and again, the bottom is going to be this yellow curve, and the Riemann man is collecting these blue rectangles. So the area of this particular rectangle A sub I would be for this particular Y sub I, going with a width change in Y. The area of that rectangle would be F of Y sub I minus G of Y sub I times change in Y. Okay? It's really not a big deal. It's just, you're going in a different direction with the Riemann man than before. So the Riemann man will run up there, accumulate all these, and I guess they're calling them delta change in I's. So accumulate all these delta change sub I's. Then we take the limit as the number of these rectangles goes to infinity. And then we get the Riemann's, or the integral for this scenario. So it'll be an f of y minus g of y dy from, in this case, let's say C to D on the picture. Okay, so C to letter D. Okay, what does the book say? The right curve, yeah, the right curve is the top curve. So you can think of that, but if you think about the orientation with the Riemann man, the right is the top, okay? If you think about how the Riemann man is running in my picture. Okay, so let's look at an easy one, example 5. They give us 2 equations in terms of y, so 3 minus y squared, and then x equals y plus 1. So you can draw these guys. Again, y squared looks like this. This is just a parabola, sideways parabola. Making it negative, we'll flip it about the x-axis, and then adding in 3, we'll shift it up 3 places. Okay, so at the end, you'll get this kind of picture. Okay, so 1, 2, 3. We have this looking picture. And then x equals y plus 1. So in this orientation with the Riemann man running like this, the slope going up we have a x-intercept at 1, and then it's going up 1 over 1. Okay, so it's going to go up in that direction, and you can kind of see the area that we're trying to figure out. So let me put that in red. Here's my region. You can put a little rectangle in there, so you can see it's horizontally, quote unquote, horizontally oriented. But if you just remember the Riemann man, you're going to get it correct. Okay, so in this case, the top curve is the parabola. The bottom curve is the y plus 1. So you go 3 minus y squared minus y plus 1 dy. And then you need the Riemann man, where is he running from? Y equals what to y equals what. So you just set the 2 equations equal to each other. Solve, so it's a quadratic, so I'm setting it equal to 0. And then factoring. And so I'm going to go from -2 to 1. And then I should be able to simplify first. Always simplify the integral before you try integrating. So I'm going to end up with 3 minus 1, so 2, and then minus y, and then minus y squared dy. And power rules, so 2y minus y squared over 2 minus y cubed over 3, and then the hardest part, for me at least, is just doing a little bit of arithmetic. So evaluate the antiderivative at 1, so I get 2 minus 1/2 minus 1/3. Then evaluate the antiderivative at -2, so I get -4 minus 4 over 2 is 2, minus -8/3 become plus 8/3. Hope that's right. Then we'll have so 2 minus 1/2 minus 1/3 plus 4 plus 2 minus 8/3. So 4, 5, 6, 7, 8. Minus 9/3 is -3, minus 1/2. So 10 halves minus 1 half, looks like 9 halves. It's a familiar answer from before. Let's see if I'm right. Yep. Yay. They note that you can actually do this with respect to x, and that's what's happening here. You don't want to do that though, and hopefully if you... So let's go ahead and redo it, and I'll show you why it's so nasty. So again, 1, 2, 3. Here's my parabola, upside down parabola, and then my line. So why is it nasty? It's because you need to work with functions, and so this parabola is actually two functions in one. So you have that red curve there, and that's that will be, and I have to solve for that for y. So I have x, I'll put it in black, x equals 3 minus y squared then equals 3 minus x. So y equals plus or minus square root of 3 minus x. So the red curve is y equals plus square root 3 minus x. And then the blue curve is y equals minus square root of 3 minus x. And then I also need to solve for the other curve, x equals 1, y plus 1. So y equals x minus 1. Okay, so to get the area of that region, you actually have to get the area of two different regions to pull this off because of the way we have these two plus and minus square root 3 minus x's. Okay, so you can kind of demark the region into two parts. There's region 1, and then over here region 2. I put 3 for some reason, the region 2. So let's put the region 1, I guess, in yellow. And then region 2 I'll put in green, so nobody's colorblind. So each one has different top and bottom curves. So region 1, the top curve, so let me do an integral for region 1. The top curve is the line y equals x minus 1. Okay? And then the bottom curve is the blue curve, the blue arm of that parabola. So it's negative square root 3 minus x dx. Okay? And plus the integral of, in region 2, the top curve is the square root of 3 minus x, and then the bottom curve is the blue arm of the parabola, negative square root 3 minus x. Okay, so it's a bit annoying, and then on top of that, you have to figure out the limits on your integrals. In other words, you need all of the intersection points. So first get this point right here. So I'll take negative root 3 minus x and set it equal to x minus 1. I need to square both sides, so I get 3 minus x equals x squared minus 2x plus 1. I get x squared, move the x over, minus x, move the 3 over, minus 2 is 0. And then I get x minus 2, x plus 1 is 0, so x is 2, x equals negative 1. So negative 1 is this point right here, so that would be my starting place. And then this is actually, I think the 2 is actually this point right here, this x value. It should be like right going through there. So it goes up to 2, and then this point right here is just 0, 3, 0. Okay, so you know then it goes from 2 to 3. Look, right? So hopefully that dissuades you from doing this other orientation. It's just a nightmare. And the book does the math there for you. I'm not going to go through it. I think hopefully just the setup was enough to discourage you from doing something that should be done in the other orientation and this kind of backwards orientation. Okay? So this orientation we just looked at is where we normally put the Riemann man getting his rectangles going like in that direction. Okay, so you literally have to do two different integrals because we have that thing that's not a function. Okay, Either way you do it, though, you're going to get the same answer, and you can see in the book they get 9/2 for their other answer. Okay, so I'm not going to bother you with it, though, and force you to. Okay, the integration is an accumulation process. So what you're thinking of is just basically what I do with the Riemann Sums, running through and collecting all of these rectangles. And yeah, that's pretty much it. Is there anything else? No, and then they go into the exercises. So let's look at some exercises and see how these go. This one, you can kind of look at the graph, but I encourage you to do the graphs and then, set the equations equal to each other and solve that way, rather than to just use the picture, because sometimes the picture can be a little bit misleading. Right? Okay, so let's take a look-see here. I guess we can do number 2. We'll make this one the video quiz as well. You write down my notes. This is now in video quiz set number 3. This will be the first question in there. And, well, actually, all you have to do is set up the integral for this one, so let's not do that one. These are just kind of thinking about it geometrically, the picture orders. It doesn't matter which orientation you do, you're going to get the same answer for these. It's a bit silly to force you to do the other orientation, and the other orientation is a nightmare to do. Let me do this one for you. So we'll make number 6 the video quiz, just because people always email me saying, I don't know how to do this one because I don't know how to use the buttons, believe it or not. So let me show you how to do this one, and I'm just copying it down so I have it in my notes that this is the video quiz. Okay, got my notes. We need to find the area, so number 6 from WebAssign, this is their video quiz, video quiz, video quiz. Okay, so first this guy, -3/8 x times x minus 8. This thing is a parabola. It's going to have intersects at 0 and then also at 8. Just set it equal to 0, you'll get that. I don't know if they need the vertex. Yeah, they probably need the vertex. So -3/8 x squared plus, I guess that would just be 3. So the formula for the vertex, if you remember from, you could take the derivative and figure it out. So let's do that. Let's take the derivative. That'll give us either the high, well, in this case, it'll be the low point, the maximum. Okay, that'll be the vertex. So y prime is -3 fourths x, and so set that equal to 0. So the vertex is at 0, 0, 0, I guess. Okay, well, it can't be at 0, 0. What did I do wrong? Oh, there should be an x. Okay, sorry. So plus then 3, and set it equal to 0, -3 fourths x plus 3 is 0, -3 fourths x is -3, x equals 4. That's the x coordinate of the vertex, and then plug it in for the y coordinate. So y, plug it back into the original equation. Y equals -3/8 times 4 times 4 minus 8 is -4. Okay, so this and this will kind of cancel. And then this and this will go in there, so -2. 2 times -2 times -3 is 6. Okay. Okay, so let's get this. It's this button we need. And then I'm gonna. I don't know how they want me to plot this. It's not so easy, is it? Okay, so I guess I gotta see what happens. No. So I want 4, 6, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. Yeah, I'm not even sure how to get it. Stupid thing to work. whatever that is. Let's try this again. 4, 6. 4, 6. Maybe you got to put more than one point in there. How about 0, 0, and then 8, 0. And this is annoying. Let me pause the video. Okay, I think I got it. So this thing has to be in blue somehow. Somehow you get it in blue. And what I did was just go to the vertex here. So at 4, 6. And then I did one other point, and miraculously it worked. Okay. Okay, so there's a vertical parabola, I guess that's what that is. Okay, so that's one of them. I also need 3 lines, I guess. So y equals 14 minus 1/2 x. So the y-intercept there is 14. So you need a double-headed arrow. So y is 14, and then it's down 1 over 2. 1, 2, right there. Just using negative 1/2 x. The negative 1/2 is a slope, right? Down 1 over 2. Okay, so there's second line. Then I need x equals 4. That's a vertical line at 4. So again, you need the double-headed arrow thingamajig. And then just go to 4. And put some dots in there. And then I need x equals 8. So again, you got to use the double-headed arrow thing, or it just won't work. So double-headed arrow. Make sure it's in blue. So where the heck is it? 8. So put some dots. You need at least 2 dots apparently. And then we need to fill in the region, I guess. Add fills last. Okay. Sketch and shade the region. So I'm going to fill in that region there. Okay. Well, that should do it. Now let's go ahead and do the integral. Okay. So we have the integral, and this time the bounds are kind of just literally sitting there with the equations of lines. For the 8, the top curve is the 14 minus 1/2 x. The bottom curve is the parabola, which is negative 3/8 x squared plus 3x. I hope this is right. And then you have this monster to do. Okay, so clean it up first. 14, we have plus minus here, so 3, so that would be 6 halves x, negative 6 halves plus negative 1/2 is negative 7 halves x, and then plus 3/8 x squared dx, and then I got to do power rules, so 14x minus 7x squared all over 4 plus 3x cubed all over 24, but simplifying, you just get x cubed over 8. And then I evaluate that on the limits. So putting in the limits in the antiderivatives. So first plugging in 8. I'm going to have to get my calculator out so I can do some arithmetic, because I don't trust myself to do it on my own in my head anymore. I've seen that go wrong one too many times. Minus 64 divided by 4 times 7. Ooh, really? Minus 112 plus 64 minus 56 minus, it's going to be n of 28 plus 64 and 8, of course just 8. Goodbye. 64 minus 6 minus 28 plus 8, 36. Minus 36, and this is where I find out I'm wrong. 8. Terminal. Oh, I got it. Sweet. Okay, so you see how those are. You have to use the double-headed arrow on the lines. People always want to use line segments. This dot dot thing, don't use that. Okay. Okay, so hopefully that's good. And then for the parabola, I had to put in 2 points, and that was enough. So I used the vertex in one of the x-intercepts. Okay. And then hopefully none of this will be too big of a deal. Oh, this one always gets people, so I'll try number 14. Find a value a such that x equals a divides the region bounded by the graphs and the two equal into two regions. Okay, so let's see. I have y squared equals 4 minus x. So I'm going to rewrite this as x equals 4 minus y squared. So 1, 2, 3, 4. 1, 2, 1, 2. So that would be a sideways parabola like this. And then we have x equals 0, such as the y-axis. So it's this region. We want to find the line x equals a that divides that region into two regions. You could simplify it a little bit. I don't know how much you can really simplify it. So anyways, we're looking for this line, x equals a, such that the area over here in region 1 is equal to the area over here in region 2. Okay? And you know, you could simplify it a little bit by just kind of getting rid of this whole bottom half and just worrying about these two regions. I don't know how much that's going to really help, but this curve right here then, you know, it's just the x equals 4 minus y squared, and then we're doing an integral from on the y-axis going from 0 to 2. So the Riemann man, the running man orientation is in this direction, and our rectangles are like that. So that you could go from 0 to 2, and we have 4, but we really don't want to do that, right? Because that's not going to do it for us. We need actually this other kind of orientation. That's what I'm going to do. There might be a different way to do this. So the top curve I'm going to make. Yeah, I can solve for y, right? So I can say y is equal to the plus or minus square root of 4 minus x. The top curve, so like this blue part, try to draw in blue, this part right here is just the plus version. So 4 minus x, square root 4 minus x. And so what you're doing is kind of, you could set up an equation with two integrals. So first the Riemann man is running from 0 to this value a that we're after. This line here, again, is x equals a. And in that case, we're integrating the square root of 4 minus x dx. And then that should equal the integral from a to this x value here, which is 4, because that point is at 4, 0, right? So a to the 4 of the square root of 4 minus x dx. And then you just integrate both sides, and you have an equation in terms of a that you can solve. Okay. So you could do a u sub if you want for 4 minus x. You get du is negative dx, so dx is negative du. So on the left here, I got u to the 1/2 times negative du. Pull out the negative, you get du like that. On the other half, you can use a different letter. There's a negative there. So you get negative u to the 3/2 times 2/3. Evaluated equals negative z to the 3/2 times 2/3. Evaluated. Back subbing now, so negative 2/3 times 4 minus x to the 3/2 equals negative 2/3 times 4 minus x to the 3/2. And of course, we still have to evaluate from 0 to a on the left and from a to the 4 on the right. You can multiply both sides by negative 2/3 to get rid of all that junk. That'll be a legal move. Then plug in 9, so you get 4 minus 9 is negative, and you can't take the square root of that. So that's a sad day indeed. That's not a 9, that's an A. Right, sorry. So 4 minus A to the 3/2 minus 4 minus 0 to the 3/2. 4 to the 3/2 is 8. And then that'll equal 4 minus 4 is 0 to the 3/2 is 0. And then minus 4 minus A to the 3/2. Okay. You can add the 4 minus A to the 3/2, so you get 2 times 4 minus A to the 3/2. Add the 8 to the other side, you get 8. Divide both sides by 2. 4 minus A to the 3/2 equals 4. Raise both sides to the 2/3 power. You get 4 minus A equals something, 4 to the 2/3. So solving for A, you get 4 minus 4 to the 2/3, and you know, whatever the heck that is, 2 decimal places they want. And so 4 minus 4 to the 2/3 is 1.48. We'll see if that works. We'll leave it at that if I'm right. If not, we have a little bit more work to do. Yay, I'm right. Okay, so that'll do it for my video. Thank you for watching, and I'll see you next time.